Hi guys, in this video I'm gonna talk about numerical integration. So we will take a look at how to integrate functions. And besides symbolic integration using calculus and all of this fancy mathematics, which isn't really efficient for a computer to deal with, we have numerical integration. It's like a toolbox of methods to use. So let's look at numerical integration in general. Let's look at some schemes, not just like the scheme that we are going to use, but in general, what schemes can be used. And we'll start off by just taking a look at a polynomial function here. So I'm just going to paste this in. So what we have here is this function, and what I want to do with this is I want to compute the integral from 0 to 3. So basically that means area, right? Let's compute the area underneath this. So, of course, we can just take and integrate this using, the fundamental theorem of calculus, and that is included in MATLAB as well. The function you have been using is called int. So you throw int at this, and you get the exact integral here and its corresponding decimal number. All right, we could use variable precision integration as well. The deal with this is that it's always going to generate a decimal type of number, and it does it numerically, but it does it with very high precision. And we can, in fact, if we go to the help file on variable precision integral here, we can scroll down to the section about these arguments, and we can see here that we can actually choose what a relative tolerance is going to be, and the absolute tolerance and max number of function calls. Those are basically how many integration points or function evaluations we are going to use. So yeah, you can read about this more, and you will understand the jargon I'm using now when I just get into this more. So when we want to talk about numerical integration, I think the best thing to do is to just look at the Riemann sum. That's like the stuff that you have been exposed to in the very beginning, is just bars, right? So we have certain function evaluations here. We have a number of them, and each function evaluation is multiplied by its width, basically the difference, the delta x. So if you take a function evaluation that's at some point and you multiply it with its width, and you do this over the whole region, you can sort of approximate a integral. And this is what the Riemann approximation is about. If we do this, we can increase the number of points, and we can see what happens here. So if I'm doing the slider, which increases n here, and I can see in real time what my approximation will yield. And with the amount of with n, I will approach the true solution. I will in fact never reach it discretely like this, but I will get there eventually. And this is very costly. You see here I have 1000 function evaluations, and I'm still very far away from, like, this is my error, so I'm going to do the absolute error here, which is quite high for 200 evaluations here. Even for 1000, I'm getting sort of a pretty large number. So let's play around with this graph. We will update it a little bit here. So if I play around with this slider here, I can sort of update my graph down below here. And yeah, so you can play around with. So basically that's the Riemann approximation of an integral. Now why do we bother with numerical integration, really? So there's several reasons for this. One of them is that our function that we have gotten here, in this case it's a continuous function, so obviously and it's quite easy to do, so we can just use the standard theorem of calculus to calculate it by hand, or we can throw the corresponding symbolical or analytical method at it in MATLAB here to get the analytical solution to this integral. Or we can use numerical integration to do that. But in this sense, it doesn't make any sense to use numerical because this method here works very fine. But what happens if we don't have a continuous function? What happens if we just have a bunch of points? and we want to integrate these points. For instance, you're measuring power consumption of your refrigerator every day, and each second you take a measurement of the power, and you want to know how many kilowatt hours are you producing. So that means that you have to sort of multiply this with time, a delta time, but it's not a continuous function. You're just sampling the power every minute or every 10 seconds or whatever. So you know the sampling frequency, and you know the value, and you can sum this up, and the summation becomes sort of this integral, but it's a discrete thing, so it's a summation, it's not really an integral. But yeah, so for those reasons we need to have a way of integrating, if you want, and basic methods are using the Riemann integral, but we can use a better approach. So that's one reason to use numerical integration. Another reason to use numerical integration, besides having a discrete function or just points that we want to integrate, is of course if we have a function for which the integral is not ordinary, or it's a standard integral. So you can have nonlinear business going on there. Non-continuous function is one of them, but they could also be, I'll show you an example of that. It could be 1 over the square root of sinus x. That's one integral for which you cannot use the standard approach, which you have learned in calculus. So you have to handle that. You can plot that function, and there is a mechanical application for where that stuff shows up. It's like if you have this pendulum and you let it go, and then you want to sort of calculate how high it gets up on the other side. So from mechanics, you can formulate a problem for which you need to solve this integral, but you can't because you don't know how to do it numerically. So these sort of problems show up everywhere around us in engineering, and we need to know what tools we can apply in order to solve them. So let's look at a better way of doing numerical approximation. So what we will be doing is like looking at how to approximate our function linearly. So just using standard linear approximation here. If we take our function f of x, and we sort of take the endpoints of it, a and b, and we linearly interpolate them by linear basis functions. And I will just denote this using phi1 and phi2, because you know what these are. You have been playing around with this. So this will essentially give us the following. So using linear interpolation basis functions here, we will get to this, which you have seen earlier. It's just we're dealing with endpoints here, so we're evaluating f in the endpoints instead of continuously everywhere. All right. So our integral can be approximated by the function evaluation in a over b minus a, and then we have this integral here plus the upper bound here, x minus a dx. So this is what we have here. So that's our that's our integral. So we're just integrating this thing here. We are integrating this function here. All right, so this thing, if we work out what this integral is, we get this here, and if we evaluate this, we arrive at this expression, and you can work it out yourself, which leads to the following here. So we're getting sort of fa over ba, and then this guy here is simplified to b minus a squared, plus this type here, which is also simplified to b minus a squared, right? So we're using standard algebra here to arrive at this. Okay, and then we can combine these, and finally we have that we have 1/2 b minus a, which is sort of half the region, right? So this is our whole complete region from 0 to 3 in this case here. And then we have half of that. So we're basically looking at the midpoint. So we have the midpoint, and then we multiply the midpoint by what? Well, our evaluations at the end and the beginning here. So this is what we get using a linear interpolation. And this thing is called the trapezoidal rule. Yeah, so our integral is sort of not a bar anymore, but it is this slanted bar, let's say. Of course, we're not going to approximate our integral only using one of these bars if you want, but we are going to do this in a chained way. So we're going to split up our range into n subdomains, and we will have n+1 evaluation points when we do this. So this chained approximation becomes this. So we have our integral from a to b f of x dx, and this becomes b minus a over 2n. So this range is split up. So this 1 over half is following here, but it's also divided by n regions. And then we have the sum of all of these. So we're adding a bunch of these together now. So for the example that we're dealing with here, we will end up with the following. This is the trapezoidal rule expressed graphically here. So we have, let's say, 8 regions. That means we have 9 evaluation points for this continuous function from 0 to 3. And you see here what the trapezoidal rule does. So if we go up here and we set this here to 8, we can sort of see the difference here. So this is very, very jagged and very imprecise. Just look at the white area here, which is sort of representing the error, and look at this area here, which is representing the error. It's quite a bit smaller. So the trapezoidal rule, while still using quite a few, or while still using the same amount of evaluation points, will yield a much better fit, or much better, geometrically much better fit. So basically a better integral, or a smaller residual or area. Okay, now we can sort of define this programmatically. So we will create our points here. So we'll have a lean space from a to b, n+1 points, and our first and last points are going to be this. So we're going from 1 to n-1. So those are our starting points, and then our end points are of course going from 2 to the end. And the integral formulation here, I_t for trapezoidal, is just the sum of f of the first, so we are evaluating the function in all of our start points, plus f of all of our endpoints, and then times the actual range here, which is varying with n. So we have b minus a over 2n, and we're summing all of these up. So we're just computing what is this area, what is this area, what is this area, and just adding them together like this. And then we are converting this into a double, because our f is a symbolic value, so we'll get a symbolic answer here. So let's take a look at that. All right, so our answer is this this fraction, and this is evaluated to this number here in terms of decimals. Now, the trapezoidal rule, you don't need to really do all of this business here, because it's built into MATLAB. It's called trabs, and what you need to send in is just your evaluation points and the actual the function evaluations. So let's go back to this example I had with the power for your refrigerator. So let's say you're sort of measuring the power for the refrigerator each second. So you're storing the amount of time in x and the actual measurements in y here, and then you can just call trabs here and you will get your kilowatt hours. So you have, wattage here, that's your power, and you have the time here, and this is basically you multiplying power with time, and you get the energy in terms of expressed in kilowatt hours. So that's when you have discrete measurements. And for this type of problem here, when we have a continuous function, of course, this is very wasteful to do. You could use other methods, but it's still, in general, this is what you have. This is the tool that we primarily use in that kind of case. So let's take a look at what the error is. So the absolute error is, of course, this value here for our 8 points. And then if you look at the actual error difference, so this is the error for our Riemann integral, and this is for our trapezoidal integral. We can see that the trapezoidal integral is actually almost 10 times better. So that's quite good. So we have an improvement of almost 10 times. Let's create this plot now, because I just pasted in this picture. So if you want to play around with this, and it's quite fun, to be honest, this is the code to do this. And I'm not going to go into detail of how this works, because that's besides the point. But this is how what you have here. And now if you just play around with the slider here, you will see that all of this. Let's remove this section here so we can sort of update everything. So yeah, so for 205 function evaluations, this is the corresponding trapezoidal. And you can see here also that the now like for 8 points we had an improvement over the Riemann integral by a factor of 10. Now that factor is actually over 200. So it's yeah, it's a quite good method, or I should say the Riemann approximation is quite bad. I mean, it's just academic for sort of learning the fundamental second fundamental theorem of calculus, and really not useful for anything else. All right, cool. We've done that. Good. Now you know how basically numerical integration works. So let's take a look at a really good numerical integration scheme, because what we have seen now isn't really impressive. Can we integrate polynomials exactly? And we can. If these polynomials are linear, then our trapezoidal rule will integrate these exactly. And really the Riemann approximation is also integrating that exactly. I'll show you in a second why. But let's take a look at the code here to make my point clear. So I have this function here. It's a linear function, 1 plus 3 times x, nothing really special. I'm integrating this from a is equal to 0 to b is equal to 3, and my trapezoidal rule states that I get this integral here, I1. That's my trapezoidal. So 16.5 here. All right. So is it true? Let's do the integration using int here and a symbolic value of f. And if I do that, I get 16.5. Okay, perfect. So it's exact. So this is the actual integral, and this is the function, and this is what we're doing. We are sort of evaluating this thing using these two function evaluations. Can we do better? What do you think? Just take a minute to think about it. The aim here, this whole exercise, this academic exercise, is about finding out the cheapest numerical scheme. And by cheap, I mean as few function evaluations as possible. We don't want to do this many times. Each function evaluation costs time. We want to keep this to minimum. So for linear polynomials, there is a cheaper way. If we evaluate the midpoint of this thing here, a plus b over 2, that is around this point here. If we take this just constant evaluation at this point here, we will actually get the exact integral. It's 16.5. So I'm just evaluating f in the midpoint, and I'm multiplying it by the range. Now, just take a second and think about why this works. So we have one function evaluation instead of two, and we're getting the exact answer. And of course, this works because we're doing the same error on both sides, and your mathematics teacher should have sort of showed you this example already. So this error that we're making on this side is the same as the error we're making on this side. Basically, we're adding too much here, and we're not adding enough here, but these cancel each other out. So that's why it works for any linear polynomial. It's not really anything to hooray over. For linear polynomials, we have cheap methods. Good. And what about everything else? That's the big question. What about for polynomials of any order? Can we have a method that not only approximates a polynomial good, but actually approximates a polynomial exactly, using the same feature here by choosing a point carefully, or a few points carefully, such that we get this feature that we're making an error, but the errors are canceling each other out. And if you think about it, maybe it's a little bit intuitive for you to think that it would be actually possible to find a certain number of points for polynomials where this actually would work, or for functions which are symmetric. If you just think about it intuitively, or make a few drawings even. And like one really smart mathematician figured this out, and his name was Gauss, because there's always going to be some of these guys involved. If it isn't Gauss, it's Euler. So one rule to rule them all, the quadrature rule by Gauss. This guy was kick-ass at what he's been doing. So the Germans actually put him on their money. So this is a 10 Deutsche Mark from a time where they actually had their own currency before moving to the euro. And this is our friend Gauss. This is equivalent to around 50 kronas today. And if you just take a look here, you see what you find. They actually put mathematics on their money and then Gaussian distribution. So if you haven't heard that the Germans are known not just for their sauerkraut, but also for their extremely good analytical skill, then you see it here. And this is from 1st of September 1999. So yeah, every child was exposed to Gauss from an early age, where you just buy candy and you give the people money with Gaussian distribution. Of course you're going to be good at math. Come on. Right, so Gauss realized this amongst a million other things. And what Gaussian quadrature is telling us is that this error cancelling property can be generalized so that n integration points integrate polynomials of degree 2 times n minus 1 exactly. Not an approximation, but exact integration. Alright, now in different textbooks you will find the Gauss, these special points which we'll be using because this is what it looks like. So for a range, and in this case I've chosen the range 0 to 1. It's not kosher to use this range, but I've chosen this because it's easier sort of to verify. I've told you about my reasons for choosing the range 0 to 1 instead of minus 1 to 1 before. But yeah, so I'm using that range. I feel comfortable with it. But I'll show you why sort of people are not liking this range soon. So we have this integral going from 0 to 1, and we have this polynomial. And really doesn't need to be a polynomial, but let's say it's a polynomial for now. And this thing is approximated by the sum of this polynomial evaluated at these points here, xi. And these points are carefully chosen. And we call them Gauss points. And then we multiply this function evaluation here with special weights called Gauss weights. And this thing for polynomial, if we choose the right amount of points, will be exact. So it will be exactly that. And that's the beauty with Gaussian quadrature and the property that we are using in the finite element method. So I have a nice table because everybody's using tables to sort of show these points here. So we have the Gauss order 1, and with the Gauss order 1 we can exactly integrate polynomial order 1 as well, and our point is going to be 1/2 and our weight is 1. So this is nothing special. So for this low order, for linear functions, this is what it is. We have this thing here, and that's not fancy at all because the trapezoidal rule does this, and even the Riemann approximation does this. So really nothing special. But here for Gauss order 2, that means our polynomial order is 2 times 2 minus 1, 3. So we can integrate polynomials of third order using 2 special points and 2 special weights exactly. That's quite something. That's cheap. So let's show this with an example. So with code we have our polynomial function here, which is just x, and we're going to integrate this from 0 to 1. Okay, nothing special here. And now we choose our Gauss point to be 1/2 and our Gauss weight to be 1, and our our approximate Gauss integral is given by this function here, x, evaluated at 1/2 times 1. I mean, it's just 0.5. So it's nothing special. Okay. So, not a big deal. After all, even the Riemann sum is exact for linear polynomials. But how about third order polynomials using only 2 function evaluations? That's got to be worth something. So what we will be getting at is that for this third order business here, we will somehow find 2 points for which we choose carefully a weight, and we multiply. We take our function evaluation at that point, and then we multiply this by a weight, which sort of can be seen as multiplying it by this sort of length here. And if you look at the table here, the weight is actually 1/2. So our length here is 1/2, and then we get this area. And now we can see here that we're overshooting here. We're quite undershooting on this side, but then we're making up for it, because here we have this small region where we're overshooting. We have this quite small region where we're undershooting, and then we have this pretty big region where we're overshooting. Turns out that this plus this tiny thing here plus this is actually 0. So we're making, we're just getting the exact integral, and that's quite amazing that it works. But let's see if it really works. So we take this example here. This is our example third order polynomial, and we will take it in code, show it here. So there's that function, and I'm gonna take the table above and just create a bunch of Gauss points in this vector form here analytically. I don't need to do this, but I'm gonna write it like this. So these are Gauss points. We have 2 of them, and then our Gauss weights. And then our integral becomes, well, our function is evaluated at the first Gauss point here times the first Gauss weight plus the function evaluated at the Gauss point 2 times the second weight. And we're getting this thing back here. And if we just do, well, we can simplify this perhaps. So if we simplify this, we get 5 over 4. And if we take this into a decimal number, we get 1.25. All right, is this correct? Well, we can take the exact integral and check it. Bam, exactly, it's exact. Okay, so how about comparing this to the trapezoidal integral? Well, it's not really fair, but let's do it. So let's take 50 points. So for 50 points, we're not even close. How about 500 points? We're sort of getting there. Still, we're off at the, what is it, 1, 2, 3, 4, 5, 5th decimal place. So 500 evaluation points instead of only 2. And we're not even close to the true solution. I mean, it depends on your application and how accurate you need it to be. So let's visualize this programmatically using MATLAB. So we can sort of throw this in here and see that this is what we have. So it's quite amazing, I would say. All right, so this is basically how this stuff works. So you can just take this and use it, but I'll show you if you just stick around for a second more. Let's go down the rabbit hole and see how this can be generalized even better. So we will now see what happens when we want to take any order, not just the tableized thing like this. You can find this in the literature as well. It's going to be for a different range. And that's also a thing, like I've actually computed this using the method I'm going to show you now for this particular range here. So yeah, so not only can you use this for any range, but you can use it for any order as well. So if you just search for Gauss quadrature, you'll find Wikipedia, and then Wikipedia is going to tell you everything you need to know about this. But you will see that there's a special algorithm that's called the Golub-Welsch algorithm, and then there's a sort of paper or report on called Spectral Methods in MATLAB, which are published in 2000, where this algorithm is originated. So this algorithm is a function which I can paste in here, And I'm gonna do it symbolically just to show you. So functions we haven't really talked about in MATLAB, but basically if you just go to the end somewhere and paste in this thing where it says function, then it is a function. We can use it as a function, but it sort of contains more code. Yeah, that's I don't know, if you want to know more about functions, like you can study this and Google it and ask me. But yeah, so this is Gauss underscore sim, so it's a symbolic thing that it's going to give us. Now, how this works is completely besides the point. This is mathematics. It's quite advanced mathematics, and yeah, just let's not go there. We will just use it. We don't care where it comes from. There's mathematicians that are working on figuring this stuff out to make our lives simpler. So let's do an example. Let's first use this and figure out what this integral is. So we're gonna use this for a third order and from the range 0 to 1. So it's gonna spit out Gauss points, it's gonna spit out Gauss weights, and it's gonna give us the range, which is basically b minus a here, so nothing special here. And then we can sort of compute this integral by using this sum here, but the sum is just a matrix or a vector multiplication. So we're sort of taking this stuff here. Let's see what the output is first. So the output is going to be this row vector, and we have a column vector here. Sorry, we have a row vector. No, we have a column vector and we have a row vector. And if we take this thing and we multiply it, we need to transpose it, multiply it by a column vector, we will get a scalar, and that's exactly what I'm doing here to get this huge thing. But then when I simplify it, it just reduces down to 5/4, what we had earlier as well. Yeah, we can use more points than that. So I can go to fourth order here. So if I do fourth order, this is what I get. I get this fraction, which isn't really nice anymore. It's very hard to express. My integral will not be more exact than this, but I can go as high as I want. I can go to sixth. I can have six numbers here and still get the same number out. So I need to have at least third order, the second order, I mean, in order to do this. But if I go to one order, the first order, I will just get 2 points. 1 point, I will get 1/2 and 1, and then I'll make an error. So this is error. There's an error in this integration. But as soon as I go to the second order here, I will get a. I will be able to integrate a third order polynomial exactly. Okay, so it works for polynomial of any order using this way here, and this is what we pre-compute this. I cannot overstate this. We will not be using this function to generate Gauss points in a for loop because it's expensive. This stuff here that happens, we're sort of solving this eigenvalue problem. That's expensive. So we are pre-computing this. We are computing this ahead of time for maybe 10th order or whatever, and then we're just storing all of these numbers. And then when we know that we need fourth order, then we grab that from a table. We just grab it from a table. That's much faster than actually computing this every time, especially in every loop. So yeah, just keep that in mind, that this stuff is not used in the looping ever. We could really change. We could have x1 and x2 here. If you haven't thought of that, like, why don't we use this all the time? It's because it's expensive. Maybe it's faster than symbolic integration, but it's still not as fast as it could be if we just keep the range constant like this every time. All right, so yeah, before moving on, let me just show you what happens if we take this range -1 to 1. Well, this simplifies a lot because you have this thing going around 0, and then all of these are sort of more they're simpler, but our range is now 2. If you take b minus a here, you get 2, so you need to take care of that, which we are anyways. But yeah, it's sort of simpler to just think 0 to 1, even if the integration scheme becomes a little bit more awkward to work with. Yeah. So I guess that's maybe one of the reasons why they use 0 to 0, 1 to 1, because you sort of have this, I don't know, these are numbers, so when you're really using this, you're not getting symbolic values, you're getting this other thing. So let me grab that. So really when we are dealing with this, we will actually have this other function which is called just Gauss, and the only difference really is that, so this guy is called Gauss, and here I'm just I modified it. I put sim here. I converted the weights to symbolic values, and I converted x here to symbolic values, but in general they are just double precision numbers, decimal numbers. So in reality this is what we are working with. Okay, now I'm not transposing this correctly because I'm sort of, yeah, I get different things here, so I need to fix that. Exactly, so they're not the same. Yeah, never mind that. Just gonna go back up here. It's just I changed that a little bit. All right, never mind that. So we'll move on, and we will do we will look at an example, a tricky example. So remember what I said about these types of functions before? They're quite hard. Well, now let's see what I really mean. So we can, like, this doesn't look like anything, right? It's like, all right, so what is this thing? So we have this integral. Okay, how big of a deal is it? Well, it turns out that this is so-called non-elementary. You cannot use standard calculus tools to solve this. Why? Well, for that you take a course in advanced calculus to find out. Basically, we can plot it, and we can see here, all right, sure, what happens when x is 0, we get sort of this infinity thing here. Yeah, sure, but still, why? Like, I can see that this obviously can be sort of, you know, I can look at it and I can sort of compute what the area here is, approximately at least. So why should I be able to do that with int? Well, I can't. So let me just color in the area here. And if I do this, I need to sort of be careful, because this happens when I want to color it in. So I'm sort of creating 1000 points here, and you want to use the area function. This is how it works. I have to have points and y points to do this. But the thing is, I cannot use 0 here. I want to use 0. I want to go from 0 to pi over 4, but I can't. If I do that, I get an error. Here, it says that division by 0. Of course it's division by 0, because I'm taking f1 over the square root of 0. That's not going to work. So what can I do? Well, I can sort of take it in small steps. I can do 0.1 here. So instead of going from, you know, the far left side, I'm sort of just computing it from here. Well, I'm not computing anything. I'm just, you know, drawing an area here. But still, you need to sort of think about that already. So there's a little bit foreshadowing of what is happening here. Okay, so let's take the indefinite integral from this function, and this is what we end up with. There's this elliptic f showing up here. This business, which we won't be going into. But yeah, this is what we have. And so there are methods of dealing with this as well, but you know, there's faster ways of doing it. We can just use VPA integral because it's going to deal with this beautifully. So bam, throw VPA integral at this and boom, you will get your solution. What's the problem? You're going from 0 to pi over 4. It's going to handle that quite well. Perfect. All right. Now try doing this with the trapezoidal rule and see what happens. You can do that as an exercise if you're inclined. Yeah, do that. Let's see what happens. I'm not going to give you any spoilers. If you want to apply Gaussian quadrature here, you've seen that we're starting using the range 0 to 1, and this is not 0 to 1, this is 0 to pi over 4. So we need to convert everything to 0 to 1. That's the reason why we've been going through this isoparametric mapping. It's for this reason we want to be able to use Gauss, but we can't because we don't have to convert everything into a range, a certain range, really any range. But yeah, we're choosing 0 to 1 in my case, but you could use the range -1 to 1 if you want. So we need to take x from general A to B and map it to the range of 0 to 1 using isoparametric mapping, and this is what we have been doing. So we take this x of this map variable here, which we call xi. We define this to be of this form because we're just doing a linear map, and its derivative, or the real map really, it's going to be just this b minus a here, and we end up with our integral, which is going to be on this form here. So we have our integral f of x dx, and that's going to from any range a to b, and this is exactly the same as the integral 0 to 1 f of x of xi, and multiply it with the Jacobian dx dxi times dxi. And this will yield the following, because dx dxi is b minus a, we have that this thing is equal to b minus a times the integral 0 to 1, because b minus a is not dependent on xi in any way. We can move it outside, and this is what we have. All right, now we can just apply Gauss to this integral, and this is what we end up with. Finally, we take our integral here, which we have, the isoparametric integral, and we have b minus a times the sum of all of the function evaluations at x of I times wi. Okay, how does this work? We can solve our problem using the Gauss algorithm now. So we take 8 points, for instance, here, 8 function evaluations. Remember, this function here is it's not a polynomial. We cannot exactly integrate this using Gauss. So we'll take, whoops, we're gonna take Gauss here. We're gonna create 8 Gauss points and 8 Gauss weights, and here they are in the range from A to B, and B being pi over 4 here. Really, I don't need to use isoparametric mapping here. I realize that now. I shouldn't be suggesting it because it doesn't really matter. I need still to generate, I still need to use this method, this algorithm, to generate all of these points, so I might as well use it for this. This is not, I'm not using this for finite element method now. I'm using it in general just to showcase how you can integrate any function. So this is gonna be more, it makes more sense to use it in a general range like this here. But that's also the only reason I'm using it this way. If this was for finite element method, I would of course use the isoparametric mapping. You can try out both. I'm gonna do it this way and showcase this to you. So I'm doing v minus a times f times f of this Gauss points evaluated at GW here, and this is what I get. So this is my Gaussian integral for this, evaluated in 8 points. I get 1.7 something. So of course I'm making an error here, as you can see. Obviously, even for 8 Gauss points, this error is quite substantial. But if I try to do this using traps, I will fail miserably because I cannot go from 0 here. A is 0, so I will get division by 0 here, and then this of course will be just infinite. So I need to do something else. I need to, you know, truncate this a little bit. So how much? 0.1. Okay, yeah, I'm sort of far away. So what happens if I go lower a little bit? Like, okay, I'm doing 0 to 0.1 instead. But then I'm going away, and the more I lower this, the higher the error here. Like really, because I'm getting this huge number in the beginning, because you know I'm penalizing myself here. So this is not a good method of calculating this at all. It doesn't really work. You cannot use traps the trapezoidal rule to compute this integral, so it's just meaningless. So yeah, so this was a special case, right? And I wasn't really using the isoparametric map here. So let's take another example, which is going to be more likely that you will encounter, perhaps. Yeah. So we will use a sinusoidal, which is not a polynomial, of course, and we'll revisit our old friend here, this function which you've been working on earlier. So we have, I'm gonna just throw this at you here. This is what we have. So we have a function and we have this cyan area here that we want to compute. Okay, so let's do that exactly. So we have our exact integral here, and we're going from this range -3 to 0.9 to just be a little bit special, but it's arbitrary. I just chosen some random points. Okay, so we have that. Now we can compute this on decimal form. This is our integral, 3.41 something. Okay, so let's approximate it using the Gaussian quadrature here. So let's see what we have here. Okay, we have 8 function evaluations, or the Gauss order is 8, and we're doing this from this range here. So using Gauss function here, again, it makes more sense because we're not in the sense of finite element method here. We're doing something completely different. So I'm not gonna bother using the isoparametric map, but we could convert this whole function into using this business here, but I'm not gonna do that now. I'm just gonna go ahead because it's quite easy. I don't bother with using this isoparametric map. All right, this is our error. Quite low. Okay, so compared to what? Well, compared to the compared to trapezoidal rule, which is quite high here. Let's do something called the error analysis. This is like sort of similar to the L2 error. So I'm gonna use this fancy notation now. So I'm creating this variable error, and I'm going to create this structure, which is basically I can do .n, and then this is sort of a variable within a variable, if you want. So it's just a notational style, nothing fancy really. But yeah, I'm just gonna throw this at you, like to show you that yeah, you can do it this way if you want. Okay, so I'm gonna do for every element. I'm gonna throw this up here and I'm gonna show you what I'm doing. So for every point in n, so I'm gonna run this using 2 Gauss points, and then 4, and then 8, and so on and so on and so on. And for every time I'm sort of doubling the amount of evaluation points, I'm gonna compute the error. I'm gonna store that. So I'm storing the error here in I'm storing the error in this error.n. I'm storing everything. I'm storing the error, the number, the point, or the evaluation points, and I'm storing the actual error for Gauss and traps. So that's what that means. First, I'm calculating the error for traps, and this is what I get here. Then I'm going to create my Gauss points for this particular region here, because I will need different amount of Gauss points every time. That's why I don't bother with the isoparametric map. If I did the isoparametric map, this would even be faster, but I'm sort of cheating them because I sort of pre-computed all of this ahead. I want to make an apples-to-apples comparison. If I actually use this Gauss function, what's going to happen? So yeah, so let's see how fast this is as well. And I can in fact do that. I can do a tick and tock here. So I'm timing how fast this traps is going to be. And I can put this into a different like a time dot Gauss, and then this could be this guy here. It's going to be the same size, let's say. So I can sort of I don't need to. I can copy this. This is going to be the same. So just a bunch of zeros. I'm pre-allocating zeros here, and then do time dot traps. Yeah, I just thought about this. Didn't think about this earlier. So yeah, now I can store this value here in time dot traps, and this is going to be I, and then I'm storing the time it takes to run this, like so. And then I'm gonna start the timer for Gauss here, and I'm gonna stop it here. Right, so I'm sort of timing how long this takes to run. But in all fairness, I need X node here as well, because yeah. So if I want to be fair to Gauss, I should really do this, because it actually takes some time to create this function here as well, which I don't need here. Exactly. So yeah. So this is more fair. Okay, and then I have time dot Gauss of I equal to talk. All right. So now I'm storing I'm storing the errors down here, but I'm also storing the time it takes to compute these integrals for 2, 4, 8, and so on, function evaluations. All right. So I run this, and I can take a look at my stuff here. So I have Gauss in here, and yeah, I'll actually plot this, but yeah. So let me plot this. So this is what I have. Let's look at the error plot first. So this is my error plot. I'm plotting the errors, and this is what they are. So I see here that the traps is sort of going down steadily, but look at Gauss, it's just plummeting. So we have 2 function evaluations, 4, 8, 16. We're down to machine precision. We cannot go any lower than this, because our computer can't see the difference between numbers at this point here. All right, so how does this look for how does this graph look for the time? So figure, hold on, and I'm gonna plot the time now. So I have time dot n here on the x-axis, and I have error dot n, and I have time dot Gauss, and these are going to be like so. And then I have the same, copying this, error n and time dot traps, like so. And I can put a grid on. I can do all of this business here as well. So this is the y label is not absolute error, it's actually time, and I can run this and see what happens. And well, yeah, this is what I get. So now I shouldn't really be doing it this way. It's not going to function the way I want it unless I run this a few times, because MATLAB will sort of run things under the hood here, and this timing is changing all the time. You see the graphs are changing here. I should really be running every run, so I should be doing 1000 function evaluations for I should run this thing here 1000 times and take the average. I should run this one, otherwise each time I run this it will change slightly. So it's not really a good analysis that I'm doing here, but you can sort of still see that Gauss is quite more slow when it needs to compute many points here. But it doesn't matter, because you see we don't need to create more than 16 points. So at 16 points we're quite faster than traps. So not only are we much more accurate than the trapezoidal rule, we are much faster as well. Well, maybe not much faster, but sort of, yeah, maybe at this time scale it's not that not that big of a difference here really, but still we're faster. You can have that. The first prize goes to us anyways. So yeah, we dove a little bit into this area here for it's way above what we need. We don't need to integrate general functions. We don't need to integrate general functions We are definitely not going to integrate these non-elementary integrals using Gauss or traps, because we don't need to. What we are going to integrate are polynomials, and for that purpose Gauss is king. It's really, really good. And well, we have shown that it's good for other things as well, but it's really good at this. So this is where it shines, and we are pre-computing this. We're not using this function. We are pre-computing it. We're using the table. This is enough to use table here. And for certain applications, the polynomial order you might need higher than third order Gauss. It depends on what polynomial order you have. Remember, when you're doing the mass matrix, you have phi times phi, and if phi is a quadratic function, then you have phi times phi, two quadratics multiplying each other, you get fourth order polynomial. All right. How about when you have right hand side in differential equation, which is of order, which is like x squared? Well, if you approximate x squared, if you approximate x, you will get phi times the coordinates xc times phi in that integral. And if they are linear, then this already is quadratic, and then you're just taking the square root of that even farther. So yeah, for some polynomial on the right hand side, which is high, you will need to integrate this using higher orders, and then you might actually need to pre-compute that using Gauss. So I would just always using Gauss. I will actually make a video on this. You need to think about that now. All right, so short story long, we have arrived at I've showed you how Gaussian integration works, and now I will show you how to put everything together and create your fully fledged 1D finite element solver, at least for ordinary differential equations, because we haven't really talked about nonlinear stuff or partial differential equations. We're gonna do that another time. All right, good. See you in the next video. Bye.